All right, problem number 50, we have two springs attached to a block. So we'll start with the force diagram. Force normal, force due to gravity. And let's see, frictionless surface. So we just have the two springs. And on the block, we just have the one spring. We only have one spring touching the block. And let's see, it says, what is the net force on a block if it is moved 15 centimeters to the right of its equilibrium position? So we're going to be stretching out the springs. And so we have the spring acting on the block. Now in this case, what it would be easiest to do is to, here we go, say block. And we'll call this spring 2. And then we'll draw a force diagram for the spring interface. And for between the springs, since we're assuming the springs are massless, all we're going to have is we're going to have force spring 2 and force spring 1. In this case, we have sum of forces in the x direction is equal to minus force spring 1 plus spring 2 equals ma, and we want to be at equilibrium, so those are 0. Telling us that the two spring forces have to be balanced. Let's see if, okay, so if they're just, what does the question ask? What is the net force on the block? If they're, okay, so we want to know what is the net force. So the net force is essentially going to be force from spring 2. In this case, we know that because we don't know what this, we're told that the force that pulled us out there is gone. And so the spring is going to cause the block to move back to the left. And since we're really only interested in the net force on the block, all I'm really interested in is what is the spring force on, or what is spring force 2? Alright, so let's substitute. We have K1 X1 is equal to K2 X2. In this case, if I were to think of this as one giant spring, the block is going to be displaced 15 centimeters. So I know that X total is equal to 0.15 meters, and X total is the stretch from spring 1 plus the stretch from spring 2. This will allow me to write, let's see, let's write 1 in terms of 2. And then substitute into our equation. So we have K1 go ahead and distribute the K. Yeah, we'll distribute the K. we'll go ahead and move the x2 terms to one side. So we'll have k1 x total, k2 x2 plus k1 x2. And then now I can write it k1 in terms of k2. So k1 is equal to k2 x2 plus k1 x2 all over x total. Or I could write that. Notice x2 is distributed across the k1 plus k2. Alright, and now to find, let's see, what else are we given here? We're given K1 and K2, and we're given the 15 centimeters. Okay. So I have this is a number, this is a number, this is a number, this is a number. That'll allow me to solve for the stretch for 2. There we go. So now that I know how much the second spring stretches out, I can figure out what that force is. So force spring 2 is equal to K2 X2, or just substitute that down, whoops, into there. And now I have a number then that'll tell me what the spring force 2 is. And that answers the question. So let me go ahead and substitute those numbers. Up. When I bring those down. 10 and 20. Okay. And which one was bigger? 1? No, 2. All right, and that'll give us, let's find, all right, got that in the calculator, and it gives you 1 Newton. So let's recap what we did here. We had 2 springs that are going to be acting on the block, though they both don't touch the block. What happens is they stretch different distances because they have different spring constants. So to start with, we drew 2 force diagrams, one of the block, and the net force on the block is just spring 2. It's the unbalanced force acting on the block in the x direction. And then we drew a force diagram between the 2 springs because we know the 2 springs don't move relative to one another at that particular point. That point's going to be, that's where they're welded together. So on one half of the point we have spring 2, on the other half of the point we have spring 1, telling us that those 2 spring forces have to be balanced. They have different spring constants, so we know they're going to move different amounts. So we have K1 X1 equals K2 X2. We know how much they move together. We just don't know how much each one individually is. So we wrote 1 in terms of 2 and the total. I substituted into my force diagram expression the sum of forces in the x direction. And what I ended up, first I solved for K1, which I didn't really need to do. I ended up actually wanting to solve for position 2 because I had all of the other numbers. I had the spring constant 1, 2, and then the total. Because once I found out how far one of the springs stretched, I could multiply it by K, and then that would give me the spring force. And in this case, since I was after spring 2, that's then being the net force, stretch 2 is what I was after. And I ended up with 1 Newton.